My name is Reagan Cox, and this is my Lab 4 for Faraday's Law. The purpose of this lab was to demonstrate Faraday's Law by observing the interaction between a falling magnet and a conductive tube of aluminum foil. My experimental time the magnet was in the tube was 1.35 seconds. The theoretical value calculated for my computational model was 1.262 seconds. Physics concepts used in this lab were Faraday's law, which relates the rate of change of the magnetic field to the electric field using flux, and induced current, the Biot-Savart law, Newton's laws, and Lenz's law, which helps determine the direction of the induced current. Moving on to the procedure, I used a magnetometer app to determine the north pole of the bar magnet, positioned the tube vertically and set up a phone camera to record the whole tube, recorded myself dropping the magnet through the tube, and then looked at the video to determine the time it took for the magnet to travel through the tube. And then I repeated this 5 times and calculated the average time. Here were my experimental results. I got an average time of 1.35 seconds for the bar magnet to travel through the tube. My computational model, I first created code for the aluminum foil tube and the bar magnet. Then I created a function for the magnetic field of the bar magnet and another function for the magnetic flux. The next steps were to calculate the gravitational force on the magnet and the magnetic force from the tube on the magnet, as well as the current in the ring. I then used these values to compute the B field at each ring and the magnetic force on the magnet. I summed up the gravitational and magnetic forces to get the total net force on the magnet. In the final step, I used Newton's second law to update both the magnet's velocity and position, and then I plotted the velocity versus time graph for the falling magnet. The computational model calculated the time of the magnet in the tube to be 1.262 seconds. Seen in my velocity versus time graph, the magnet's velocity first decreases rapidly and then reaches a plateau. Now for the interpretation of my model, the red current was clockwise and the blue was counterclockwise. In the given code, the rings with the current greater than 0 were colored red, and the rings with the current less than or equal to 0 were colored blue. Using Lenz's law, we know that red represents clockwise and blue represents counterclockwise. If the magnet was flipped, we know that the current would flow in the opposite direction. Also, in my real-world experiment system, the time the magnet spent in the tube was greater. The computational model doesn't take air resistance into account, which therefore reduces its accuracy. As I previously mentioned, the velocity in the velocity versus time graph initially decreases and then plateaus. Plateau indicates that the magnet is no longer accelerating and therefore the net forces acting on the system equal 0. Finally, the first what-if question asks what would happen if the conductor's resistance was drastically decreased. Because the current is equal to V over R, the current would increase. This would result in the magnet falling slower with a decreased velocity. The second question, if holes were cut into the tube, there would be fewer rings and the induced current would decrease. A lower induced current would lead to an increase in the magnet's velocity and a shorter fall time. That's it for my lab.